Hi kids, this is William from Beyond Infinity. Have you ever encountered math problems that you just don't know how to solve? How about I teach you a way to find the answer to these difficult problems? It's called making a guesstimate, and we'll be using tables as a tool to help us to do that. Are you ready? Let's get started. Believe it or not, it is very common to face math problems that we don't know how to solve. Sometimes it is just that you haven't learned the proper way to solve it, but often there's simply not an analytical way to solve these problems. So learning how to solve problems that you don't know how to solve is very important. Take a look at this example here. There are three consecutive numbers. Their product is 336. What is the smallest of the three numbers? Now, firstly, for those who don't know, consecutive just means that they are next to each other. So, for example, 1, 2, 3, or 4, 5, 6. Now, you might not even know how to start this problem. If you know algebra, you might be tempted to try algebra. If the first of the three numbers is x, then we can say that x times x plus 1 times x plus 2 equals 336. But even if you know algebra, this equation is not a straightforward one to solve. So, are there any other ways? Well, how about just taking a guess? And you might say, all right, I'll just guess, is it 13? No, it's not 13. We don't really want a random guess. A random guess is not going to get you anywhere. What we want to do is to make a guesstimate. Guesstimate. Is that even a word? The truth is, not really. It's made up of a word combining the word guess and estimate. What it means is that instead of a random guess, you make an educated guess. You use a guess that takes into account all the information that we have, and that will give us an estimate that narrows down or closing in onto our true answer. It's similar to saying if you were to guess the age of a year 5 student, you wouldn't be guessing 30, right? You would guess somewhere between 8 to 12 because you know that that is around the age someone might be in year 5. Let me show you how we can apply the method of guesstimate into solving math problems. Let's look at the question again. Apart from the fact that there are three consecutive numbers, the other key bit of information is that their product is 336. How might this help us? Well, we know that 10 times 10 times 10 is 1,000, which is larger than 336. So this tells us that the three numbers must be less than 10. We also know that 5 times 5 times 5 is 125, which is smaller than 336. So the three numbers must be larger than 5. We now have narrowed down our range from any random number to a number between 5 and 10. This is now a range that is acceptable for us to start guessing, since even if you guess wrong, you can just repeat and you'll be sure that you'll get to the right answer after only a few tries. So let's take our first guess and say the first number is 6. Then 6 times 7 times 8 equals 42 times 8, which in fact is 336. So we have quickly, with a bit of luck, arrived at our answer within the first guess. Isn't that neat? You have just found the answer of a problem even though you have no idea how to solve it. By estimating a range that our answer should lie within, we get to our answer very quickly. Now, not all problems are easy to have a narrow range identified. That would mean that more guesses would be needed to arrive to an answer. For these kind of problems, a table which lists out all of our guesses in a nice and neat way will help us in sorting out our guesses and maybe finding pattern that would lead us to an answer quickly. Let's look at our next example. We have two barrels, a red and a yellow, each have some diesel in it. The red barrel is holding twice as much diesel as the yellow barrel. And if we now pour 230 liters of diesel from the red one to the yellow one, the yellow barrel now has 80 more liters than the red. How many liters of diesel is in the red barrel at the beginning? Okay, so this problem mathematically is an easier problem to solve than before. You may be able to use algebra or maybe use bar method, which I have gone through in my last video, and you should totally check that out. Anyways, let's suppose though that you have no idea how to solve this problem mathematically. So what will you do? Let's start guessing with the help of a table. Here, we'll need to guess what's in the red barrel in the beginning. To help us sort out our guesses, we would also need to all of our related information, which are the amount of the yellow barrel at the start, the amount in the red and yellow barrel after the transfer of the diesel, and finally, the difference between the yellow and the red barrel after the transfer. Okay, so let's start with our first guess. There's no clear information that gives us a range in this case for our guesses, but we know from the 230-liter diesel transfer that the red barrel should have quite a bit more than 230 liters. So let's start with something bigger and a number that is nice to work with, say 500. Then, since the red barrel is twice the yellow barrel at the start, we know that the yellow barrel is 250. After the 230-liter diesel transfer from the red barrel to the yellow barrel, the red barrel now has 500 minus 230 equals 270 liters, while the yellow barrel is 250 plus 230 equals 280 liters. The difference between the two is now 210 liters. We actually want this difference to be 80, and so we're getting way too much. So this guess is incorrect, which is okay. Let's go for our second guess. Let's decrease our guess by 100. It is important to do your increase and decreases using a regular step. We'll see why later. So let's have our second guess as 400 liters. Then the yellow will be half of that, 200 liters. And then after the transfer, the red and the yellow will be at 170 liters and 430 liters, giving us a difference of 260 liters. This is even more than before. This is telling us that we're going, unfortunately, in the wrong direction because we're getting further away from our answers. So let's go back to 500 and have our next guess increase by 100 to 600. We can do the calculation again for each column, and at the end, we'll find that the difference is 160 liters. We're getting closer, so that's good. We can then move on to our next guess, another 100 to 700, and do the calculation again, and we'll end up seeing that the difference is now 110. We're getting closer and closer to where we want. Now, before we move to 800 as our next guess, let's review our guesses. Take a look at the last entry. We have increased our guess of the red barrel by 100, and the difference between the yellow and the red at the end has been reduced by 50. We saw the same thing when we decreased our guess from 500 to 400. In that case, we have increased the difference by 50. Similarly, going from 500 to 600 decreased the difference by 50. So we are seeing a pattern here. Every 100 that we increase in the red barrel at the start, the difference between the yellow and the red will decrease by 50. So that means that every increase in 10 in our starting value will decrease our difference at the end by 5. Hence, the decrease from our last guess of 110 to 80, we need to increase our starting value by 60. So that means that if we guess 760 here, and we can do the appropriate calculations, and we'll find that at the end, we indeed get the difference of 80, which is what we want. So 760 is the answer. We can call this technique of slowly guessing your way to the answer as estimating in regular steps. You're changing the steps in a regular way so that you can find some sort of pattern later on. Now, because we're relying on pattern to form, we need to do quite a few guesses to get to our answer. So in most cases, guessing with tables like this is not the quickest way to get to the answer. So when you look at a problem or approach a problem, first look and see if you can solve it by any other way. Only when you don't know how to solve it that you should use the table and guess. But there's a catch there, because there is actually a class of special problem that could actually be easily solved by a special way of guessing and tabling. In fact, for those problems, it is much easier to solve using this than using proper algebra. Let's look at an example of that. A farmer is counting rabbits and chickens in her barn. She counted 10 heads and 34 legs. How many rabbits and chickens does she have? Well, if you've seen my previous videos, you would recognize that this is in fact the famous chicken and rabbit problem. This type of problem is also known as sums and differences problems, as here we have two sums, the sums of the head and the sums of the legs. And there's also a fixed difference, the difference in legs between rabbits and chickens. We can solve this problem easily by drawing up a table of chicken, rabbits, and the number of legs. We first assume one extreme, that all of the animals are chickens. There would then be 10 chickens, no rabbits, and we only get 20 legs. We then apply the fixed difference. Each rabbit has 2 more legs than chickens. And so, to get from 20 legs to 34 legs, we need 14 extra legs. Therefore, we need to change 7 chickens to rabbits to get those 14 extra legs. This means that we will actually have 3 chickens and 7 rabbits, and we'll see that this gives us 6 plus 28 equals 34 legs. So what we're doing here is first estimating from the extreme, assuming everything is one type, and then solve the problem in the second guess by applying this fixed difference between the two types of items. The cool thing about these type of solutions is that it can be applied to a wide class of sums and differences problems. It doesn't have to be farm animals. Let's look at a non-farm example. A collection of 30 coins consists of 10-cent coins and 20-cent coins and has a total value of $4.30. How many of each type are in this collection? This question looks and feels very different to the one that we just solved, but it is actually the same. We have two types of items, 10-cent coins and 20-cent coins. We have two sums. There's 30 coins altogether and the value of $4.30. Finally, we have a fixed difference. The value difference between the 10-cent coin and the 20-cent coins is always 10 cents. So with these three elements, we can apply the same guesstimate technique as before. We draw a similar table, 10-cent coins, 20-cent coins, and the total value. We then first guess that all of our coins are 10-cent coins, which means there are 30 10-cent coins, 0 20-cent coin, and that gives us $3 in value. Now for each 10-cent coin replaced by 20-cent coins, we're going to get 10 cents of extra value. And from $3, we are $1.30 or 130 cents away from the $4.30 that we need to get to. This means that we have to change 13 coins from 10 cents to 20 cents. This would give us 17 10-cent coins, 13 20-cent coins, and the total value would be $1.70 plus $2.60, which gives us exactly $4.30. So 17 10 cents and 13 20-cent coins is our answer. That's neat. Any problem with sums and fixed differences, You can solve it easily with guesstimating and table method. Now, the powerful thing about tables is that it lets you visualize your problem, and that it is true for many types of problems. So even if a problem doesn't fit the examples above, you might still use a table to help you visualize your guesses and your workings. Let us look at how we use tables in these situations using a final example. Each day, Merlin places the same number of flowers, at least one, at 3 temples. To get to any temple from another, he crosses a magic river once. He also has to cross a magic river once to get to the first temple. Each time he crosses a magic river, the number of flowers he has doubles. He has no flower left when he leaves the third temple. What is the minimum flowers he must have at the start? This is actually a question from the Australian maths competition, and it is one of those questions where you look at it and you would probably think, I have no idea how to do this. But this is exactly what tables are for, to systematically guess your answer out. So let's look at this question again. The key points here are that he's placing the same number of flowers at each temple and that he has no flower left when he leaves the last temple. So we could probably work this out backwards by guessing what flower he had left at the last temple and then work out if it fits what is described in the question. So let's draw a table with what we have at the final temple and what we have before crossing River 3 and what we have at the second temple before leaving the flowers there, before River 2, at the first temple, and finally the number of flowers before crossing the first river, which is of course what we have at the start. To start our guess, there are 2 other pieces of information in this question. Firstly, we know that each river that he crosses, the number of flowers in his hand doubles. Since we can't really break a flower in half, this means that whatever he has at the last temple must be even. We can't double a whole number to get to an odd number. This point is very important, as we will see later. The second piece of information is that the question is asking what is the minimum number of flowers Merlin must have at the start. That means we must start our guess small, so that we are at the minimum. So, with this in mind, we can start our guess with the smallest even number, 2. If we guess that Merlin put 2 flowers at the final temple, then that means that before he crossed River 3, he must only have 1 flower, in order for the river to double it to 2 for him to leave all of his flowers in the third temple. Now, if he have left 2 flowers at the third temple, then according to the question, he has to leave the same number of flowers in the second temple. This means right at the second temple, before he put down the flowers, he must have 3 flowers. In that case, before he crossed River 2, he must have half of what he has at the second temple. But 3 can't be halved. 3 is not even. So we can't continue our calculation, which means that 2 is not a correct guess. Let's try the next even number, 4. If we start with 4 flowers, then we have half of that, which is 2, before River 3. We have to leave 4 flowers at the second temple, so he would have 6 flowers there, which means that he would have 3 before River 2 and therefore 7 at the first temple, since he had to leave 4 there. And at this point, again, the number is odd and we can't divide it by 2, so it's not correct. The next guess is 6, which gives us 3 before River 3 and 9 at the second temple, and again, not even, we can't half that. The next guess is the next even number 8, which gives us 4 before River 3, 12 at the second temple, since we have to leave 8 there, 6 before River 2, 14 at the first temple, and finally 7 before crossing the first river. We have finally arrived at the start. with 7 flowers in our hand. So the answer is 7. Can you see that? Even with a problem that you don't know how to solve, by guessing the right way, you can still arrive at the answer. So if there's one thing that you take away from this video, remember this. There's no need to be scared or panic with math problems that you don't know. Just breathe, visualize the problem, and if all else fails, guesstimate. So, let's recap. We've learned about how to guesstimate the answer of a problem with a table as a tool to help. If you're guesstimating, first see if you could establish a range to narrow down the number of guesses you need to make. Look at the problem and see if it is a sum and difference problem. If it is, assume everything is one extreme and then figure out how many you need to swap to make up the differences. And finally, if none of these works, guess in regular steps and try to spot a pattern to get you to the right answer. And remember, a table can be used to list out your guesses systematically or visualize the problem, so don't be afraid to use it. That's all from me today, folks. If you're keen, try out this problem by guesstimating with tables. I'm William, and this is Beyond Infinity. I'll see you in the next video.